Hey there, class. We're here today looking at going down the rabbit hole with free body diagrams. When we draw a free body diagram in this class, you will be asked to completely draw the free body diagram. And by completely, what I'm really referring to here is actually a 99.91% complete free body diagram. What I want to take is you're going to travel down the rabbit hole a little bit with me and understand a little bit of why, when we talk about a complete free body diagram, why we really don't mean really complete. So we don't concern ourselves with a lot of things, a lot of forces here, and that when we say complete, 99.91% is complete enough. So let's get over and talk a little bit about why we do that. Now, I guess the first thing I want to make a mention of is we're going to come up with a situation here, and this situation may seem absolutely ridiculous that it's so defined, but that's just the point that I'm trying to make here, is that to truly draw a complete free body diagram, including absolutely every force, we'd have to consider absolutely so many situational things that it becomes mind-boggling. So I want to be very clear from the get-go, this does not include everything we could possibly include. This is just a kind of a survey to show you that basically how ridiculous this could get. So I want you to consider the block, this little block right here on the Earth, and it's a certain size, 30 by 30 by, that's supposed to say 30, I don't know what happened there. And it's sitting still, so it's not moving. It's on the equator, and it's at noon at the equinox during a total solar eclipse. The atmosphere is at standard temperature and pressure, and the block is neutral in charge and not as affected by magnetic fields. Again, that sounds ridiculous to kind of define this out this way, but you'll see why in a little bit. We've done that. And again, I want you to be very clear that we're not going to concern ourselves with all these forces on a normal basis. All right, so let's actually draw a free body diagram of the object here. So first of all, not everything here is really drawn to scale. In fact, it would be very difficult to do that. But if we wanted to consider ourselves with the big forces here, we have the gravity that the Earth has attraction for the block, and it's in a downwards direction. We also have the table pushing upwards on it. We call that the normal force. Because the moon is directly overhead, it's going to actually attract the block upwards as well. And that's what I've called here the force of gravity 2. That's on the block due to the moon. The sun is also over here. Again, not to scale here in any way, shape, or form, but the sun is over here. And that sun also attracts it up. Now, one of the things I want to make a mention of here is why we had to talk about this being at the equinox, okay, during a total solar eclipse, is that if the moon is over, like in this position over here, okay, and the moon is not there, then it actually pulls it in this direction. So it's no longer in a vertical direction. Likewise, if it's not noon, the sun is actually not overhead, and again, it's pulling it off in some random direction like this. So the simplification we've made here is at the equator during a solar eclipse. Any other time of the year, and all of a sudden, this force right here and this force right here are no longer vertical forces. They are going to be non-vertical forces, and that changes the situation. Okay, next, we have concerned ourselves here with force on the block due to the atmosphere. This is known as buoyancy, all right, the buoyancy force. And this is a true force. The buoyancy of an object does, in fact, it makes it float, okay? Now, of course, the buoyancy due to the atmosphere doesn't make this float in the air, not like if we were to, let's say, put it in water, but it does exert a force upwards on this object. And so that does actually include another additional force here. So next up, I'm actually going to go ahead and calculate out the various effects that these things have. I'm not going to spend a lot of time talking about the the actual calculations themselves, because you can, of course, pause the video and really look at that. That's not the point of this video. It's not to teach you how to do these calculations. The idea is to show you how ridiculous this is if we start to consider all these forces. So basically what we find out is the moon's gravitational attraction is this value right here. We actually find that the sun's gravitational attraction is this value right here. The Earth itself, and by the way, this isn't even completely correct. I should be really using this equation here with the radius of the equator, but basically, it ends up being about 26.5 newtons or so. The buoyancy force, again, due to the fact that the object takes up a certain volume in the air itself, the buoyant force ends up being about, looks like, what is that, 32 thousandths of a newton. We also, what I've done here is I've taken the effects of the moon, the sun, and the atmosphere. Those are those three small components. I've added them together right up here on the top, and then divided it by the big two. That would be the normal force and the gravitational force, and found out that it's only about what is that, 0.09%, okay, 0.09%. So again, to show you the ridiculousness, do these forces exist? Absolutely they exist, but they are not big enough to ever really consider in a problem. Something else that a lot of people always want to include here is they want to talk about air resistance, okay? And again, to show you how air resistance is something that we really need to be concerned with, or not to be concerned with, and why it's not. First of all, we have to concern ourselves with the shape, okay? Is it a circle shape? Is it an airfoil shape? Is it a bullet shape? Is it a prism shape? What kind of shape are we dealing with? So the actual shape, and then, of course, this assumes, let me get a different color here, this assumes that the object, in this case, is moving through the air in this direction. Okay, again, it would be going through this way. If this moves in a different direction, well, guess what? This drag coefficient doesn't apply anymore. So the direction at which it travels through the air is important here. Also notice in the equation that the amount of drag that's on an object is also dependent on the square of the velocity. So every time our velocity changes, the amount of drag changes as well. Now, to truly solve this, you need to apply concepts of calculus. And again, being an algebra-based class, that's not going to happen in this class. So again, as we look at this situation, as far as I'm concerned, in this class, we're not going to worry about buoyancy. So this force goes away. We're not going to worry about the force of gravity that other objects have on it. So this force goes away. The force of gravity by, again, another object, it's going to go away. And again, there's other forces that we can consider. We could consider if this thing is a charged object, okay? Is this a charged object, and does it have, is there some kind of thunderstorm going by, okay? And where this is, maybe some, I don't know, I don't remember exactly. Is it some kind of positively charged thundercloud that goes by at the moment, and it's starting to maybe attract it or repel it? Again, these are all things that are true forces, but they only play such a small percentage of the overall force that we basically say, the word we use in physics is negligible, all right? So if something is negligible, we basically say its effect is so small that it doesn't matter. And that's going to be the case with pretty much all of these extra forces that, again, we're just not going to consider. Okay, so here's a general summary of the problem. When we're drawing a free body diagram, know your context, okay? Know the context. It's so important to understand the context in which you're solving. But in general, a complete free body diagram, again, complete, I'm calling it a 99.91%, is sufficient enough to be considered complete. Okay, so some things we're going to ignore, or things that we say are negligible, is gravity from other planets. Okay, unless the problem itself is about gravity, then the gravity from other planets is negligible. Basically, then the only gravity we're concerned ourselves with is the gravity of probably Earth, because that's the object that most likely we're dealing with. Again, it's all about the context. Again, in the situation we looked at, the table itself is a mass. It attracts the block downwards as well. It's very small, okay? It's very small compared to the gravity that the Earth has. So again, we ignore that. The force of buoyancy. Again, generally speaking, if we're dealing with something in the atmosphere, that force of buoyancy probably pretty small, unless it's a very big object that's very light. Chances are buoyancy is not that big of a deal. Again, know your context. The drag force, okay? Again, why don't we use this? Well, because this is an algebra-based class, and this requires calculus to actually solve it. So basically, the drag force, air resistance, is probably going to be ignored in most cases. The only time maybe it wouldn't be is if you're told that it's some kind of constant value that you're given in the problem. So again, know the context. Friction. In most cases, we probably ignore friction. Now, of course, I feel like I'm saying this a lot, but know your context. If the context is about friction, if friction's part of the context of this problem, the situation, then of course you need to worry about that. Electrostatic forces. This would also include other things like magnetic forces, other field forces, okay? Probably not going to come into play. Again, know your context. So basically, again, a 99.9% complete free body diagram is going to include the big forces that really make a difference on a daily basis.